Cosmology is, in essence, a science of light. Everything we know about the distant universe comes from the radiation that reaches the observer and from the way that radiation is interpreted. We do not observe cosmic space directly, we do not touch galaxies, and we do not measure the past of the universe immediately. We observe only light, and from light we deduce distances, velocities, masses, temperatures, epochs, and cosmic histories. In this sense, cosmology is first a science of signal and only afterwards a theory of the universe. This observation has a profound consequence. If light is the only mediator between the observer and the universe, then every cosmological construction depends on the way we interpret that light. The redshift of galaxies, the cosmic background radiation, the brightness of supernova, and the distribution of cosmic structures are not the universe itself, but the forms in which the universe becomes observable. Therefore, any cosmological theory is inevitably also a theory of the relation between reality, measurement, and interpretation. The standard cosmological model interprets the redshift of galactic light as the effect of the expansion of the universe. This image imposed itself through its mathematical and observational success. Yet the direct observation is not expansion itself, but the modification of the frequency and wavelength of the observed radiation. For this reason, the question remains legitimate whether the same observational relation may admit another geometric interpretation. The pages that follow explore such a possibility, the description of the universe through a global process of contraction of the cosmic scale. In this framework, light is no longer only a messenger of distant objects, but also the expression of a relation between two distinct cosmic states, that of emission and that of observation. The photon no longer appears only as the local product of a quantum transition, but also as the observable sign of a global evolution of the universe.
In quantum field theory, the photon is the elementary excitation of the electromagnetic field. It can be emitted in well-known local processes: atomic transitions, breaking radiation, particle-antiparticle annihilation, or other quantum interactions. From this point of view, the mechanism that creates the photon belongs to local physics and is described by the laws of electromagnetism and quantum mechanics. But the observed frequency of a photon does not depend only on the local act of its emission. Between the moment of emission and the moment of observation, the photon traverses the universe. What reaches the observer is no longer only the signal of the source, but the signal of the source after it has crossed a certain cosmic evolution. Thus, the observed light contains not only information about the object that emitted it, but also information about the relation between two states of the universe. The fundamental relation of observational cosmology is 1 plus z equals lambda obs lambda m, 2.1, where z is the redshift, and lambda m and lambda obs are the wavelengths at emission and at observation. This formula is an observational fact. By itself, it does not say whether the universe expands or contracts. It says only that between emission and observation, there is a measurable ratio. If the universe is characterized by a cosmic scale RT, then the same relation may be written as 1 plus z equals RTE RT0, 2.2, where TE is the moment of emission and T0 the moment of observation. In this form, redshift appears as the expression of the ratio between two states of the universe. From this perspective, the photon should not be understood as an object that stretches in itself, but as a signal that encodes the difference between two states of the cosmic scale. Thus, light may be regarded as the image of cosmic evolution. It shows not only what is distant, but also what has changed between two epochs of the universe. Chapter 3: Universal Contraction and the Role of the Speed of Light. In modern relativity, the speed of light c is not only an experimental constant, but also a geometric constant. It defines the structure of light cones and the limits of the causal propagation of information. Any cosmological theory must therefore respect the structural role of C. In the approach proposed here, the universe is described by a cosmic scale RT that decreases in time. The simplest expression of this evolution is an exponential contraction, RT equals R0 E minus CT. 3.1, where C0 is the rate of cosmic contraction. From this there follows 1R dr dt equals minus C. 3.2, this is a familiar mathematical structure, but interpreted here with the opposite sign, not as expansion, but as the continuous decrease of the scale of the universe. If redshift is defined by 1 plus z equals RTE, RT0, then contraction naturally produces a redshift for signals coming from previous states of the universe. Redshift thus need not be interpreted exclusively as the effect of expansion, but may be understood as the sign of a change of scale, regardless of the direction of that change. In this framework, the speed of light remains locally constant and continues to define null propagation. Contraction does not modify the local structure of light cones, but only the global relation between space, time, and scale between two cosmic epochs. In other words, c is not the speed of contraction, but the geometric constant by which light makes this evolution visible. It follows that light should not be interpreted as an object deformed by the universe, but as an observable relation between two states of the universe. In this perspective, electromagnetic radiation becomes the form through which cosmic contraction becomes intelligible. Recent observations carried out with JWST have brought back to the foreground an important problem: the existence of galaxies, active nuclei, and structures that appear too mature for the epoch in which they are observed in the Standard Model. In an expanding universe, the formation of structures is a gradual process, limited by the cosmic time available. In a contracting universe, the situation may be viewed differently. If the average density of matter depends on scale, as ρ proportional to r minus 3 of t, 6.1, then the decrease of RT implies an increase in effective density. Gravitational processes of collapse and aggregation may become more efficient. In the linear regime, the density contrast delta evolves according to delta plus 2h delta minus 4 pi g rho delta equals 0. 6.2. If h less than 0, the term that in expansion acts as friction changes sign and may accelerate the growth of perturbations. Thus, in a contracting universe, the formation of structures may become faster, and the mature objects observed at high redshift no longer automatically appear paradoxical. This reinterpretation does not yet solve all the details of structure formation, but it offers a conceptual framework in which JWST observations may be read more naturally. A contracting cosmology modifies not only the interpretation of redshift, but also the perspective on the relation between observer, reality, and measurement. Length, time, and mass no longer appear as absolute entities, but as relational magnitudes depending on the cosmic state. In this framework, the universe is no longer a fixed stage, but a process of transformation of scale itself. The observer is not external to this evolution, but part of it. The observer's instruments, body, and standards participate in the same cosmic structure. This conclusion has a major epistemological consequence. Cosmology has no direct access to the universe in itself, but only to the forms in which the universe becomes observable through light. Light is not just one physical object among others, but the universal medium of cosmological knowledge. In this sense, contracting cosmology is not only a geometric alternative, but also an attempt to clarify the difference between observation, inference, and interpretation.